Welcome back, students. In the previous videos we talked about reflection of light and we did a few problems to elucidate the concept of reflection. Today in this video we are going to talk about refraction of light. So refraction is different from reflection, because in reflection, light travels in the same medium. Like if I have a mirror, then if I take a ray of light, then it hits the mirror and then it gets reflected and then travels in the same medium, which is in this case the air around the mirror. But in refraction, that is not the case. Light travels from one medium to another medium. And when it does that, what is it going to do? And that is a study of refraction. In reflection, light travels in the same medium. It just gets reflected from the surface. It doesn't travel into the mirror. It gets reflected from the surface of the mirror and then travels in this direction. So this is reflection. Reflection takes place in the same medium. Refraction takes place in two different mediums. Air to water, or air to glass, or air to glass to air again. If you have a lens, for example, light travels from air into the glass, and from inside the glass it comes out into the air again. So there are two interfaces when you talk about a lens: air, glass, glass, air, or air, water, and water to air again. Like if you have a glass of water, then it is slightly different. If you have a glass of water, then air to glass, glass to water, and water to glass, and glass to air again. So there are basically three mediums in this example. So refraction takes place when light travels from one medium into another medium. So like reflection, refraction also has a law of refraction given by Snell. Snell's law of refraction. He says this: when light travels from one medium to another medium, and there is an angle of incidence between the normal at the point and the incident ray, so you'll have an angle of incidence, and into the medium there is a refracted ray, and the normal goes into the medium, and there is an angle between the refracted ray and the normal again, so that is called as the angle of refraction. Let me draw the picture. So I have two mediums. This is medium 1 and this is medium 2. So this could be air and this could be water, or any other thing, glass, anything. Or this could be vacuum and this could also be air. Okay. So you have two mediums. This is interface. So this surface is the interface between the two mediums. So at every point on the interface I can draw normal, right? Depending on the shape of the interface. If it is a plane interface, then the normal will be parallel. All the normals that you draw at every point will be parallel. But if it is a curved surface, then the surface is kind of curved, like this. The surface is curved. So this is medium 1 and this is medium 2. And at every point you will have different normals now. Okay? You see the normals are not parallel. Normals will be here. Air is medium, water is medium. This is medium 1, this is medium 2. So if I take a point on that, on the interface, then I can draw a normal, which is in medium 1 and also in medium 2. So this is a normal. Okay. Now there is an incident ray at this point where I have drawn the normal. Say this ray hits here. This is called the incident ray. So like reflection, you can measure the angle between the normal and then the incident ray I. That's a ray. Okay. So the angle between the normal and the incident ray is called as the angle of incidence. Okay. And what happens is the ray just does not travel straight here. It tends to bend, okay, either towards the normal or away from the normal, depending on these two mediums. We will talk about that a little later. Then there is a diffraction that is taking place. So this kind of, it's like this. The ray should have gone like this. The ray should have gone like that, but it doesn't go like that. It bends towards the normal in this case. It need not bend towards the normal, it can also bend away from the normal. But what happens is when it hits the normal at an angle, then instead of traveling straight into the other medium, it bends towards the normal either way or can bend away from the normal. Can do both. Okay. So now this is called the angle between the refracted ray, I will call this as capital R, the refracted ray, and the normal is called as the angle of refraction. So this is the angle of incidence and this is the angle of refraction. And just as we discussed in the case of reflection, these three, incident ray, normal and the refracted ray, they must lie on the same plane. Meaning, if this is the interface, this is one medium, it's another medium, then if this is incident ray, this is incident ray, so there's a normal here, so a normal that goes down. So there's a plane, you can imagine a plane. And the refracted ray must lie on the same plane. Okay? Suppose, imagine that this is a plane. Okay? This is the vertical plane. So here is the interface. So this is a normal and this is the incident ray, and inside there is a refracted ray. Notice that the incident ray, the normal and the refracted ray, all of them lie on this vertical plane. It cannot hit here and then refract at an angle. If it, suppose this is the ray, okay, so it's coming here, okay, it hits at the center. It has to be like this. It has to, the refracted ray has to go like this. It cannot go like this. Even though you can say that it can still make the same angle, whatever angle that you're talking about. So it cannot come like this and refract like this. If it comes like that, then it has to refract like this. So the angle will be made on the same plane. Whatever plane these two are on, this will also on the same plane. This cannot just refract like that. It has to be, cannot refract like this. Just like reflection. So you have an angle of incidence, you have an angle of refraction, and the incident ray, the refracted ray, and the normal, they all lie on the same plane. So this is understandable. And Snell also added one more condition. He said, well, if this is medium 1, this is medium 2, then if I change this I, clearly R will also change. The angle at which I hit this point, with respect to the normal, will decide the angle at which I will have the refracted ray. Okay? This angle decides this angle. If this is more, this can also adjust accordingly. If this is less, then this will also adjust. So there is this, if I change I will also change. But he said something. He said that the sine value of the I incident angle and then the sine value of the angle of refraction, this ratio is always a constant for these two mediums. Okay? So this you call as a refractive index of 2 with respect to 1. This is mu is equal to mu 2 1, meaning the refractive index of 2 with respect to 1 when you have two mediums here. Okay? So this is Snell's law. These three things, I, R and N, they must lie on the same plane, and sin I divided by sin R is a constant. So if it is 30, then it can have some value. If it is 45, then this value will adjust in such a way that sin I by sin R will be the same in both cases. Whether I hit it with 33 degrees or 45 degrees, sin I by sin R will be a constant. So this is what is called as Snell's law of refraction. Okay. And there is one more thing about this. I have talked about this, right? Light traveling from medium 1 and entering into medium 2. Okay, this is a different medium, right? It's a different medium. This is air and this is water. But what if light travels from water and enters into air? What will happen if I reverse the direction? Rather than light coming from air into water, what if I send light from water out into the air? It turns out that this will retrace the path. If I send light in this direction along this line, then in air it will retrace the path in this way. So you notice here, now this becomes the angle of incidence, and that becomes the angle of refraction, right, when light travels from here. So the light just travels back, it retraces the path. Okay. If I send it at this angle, then it will be R, like that. If I send it in this angle, then it will retrace the path. Okay. In that case, you see, I will get sine. Now you notice. Now sine. Now what is this? I, sine I, then sine R must be equal to 1 by mu 2 1. Or I'll do it slightly better. Okay. So this is equal to the refractive index of 1 with respect to 2. Refractive index of 1 with respect to 2. See, this is refractive index of 2 with respect to 1. And this one is refractive index of 1 with respect to 2. And this is equal to 1 by mu 2 1. So mu 1 2 is equal to 1 by mu 2 1. And it will retrace the path. So if I send it from medium 1, if I send the ray with this angle, it will refract with this angle. And from medium 2, if I send the ray with this same angle, then it will refract with this angle. You notice here, in this case, the first case, when it travels from air to water, then this ray, rather than going straight, it bends towards the normal. Okay? Here, when you send the ray from water to air, instead of going straight like this, it bends away from the normal. See? So the bending can be either towards the normal or away from the normal. It depends on what you are entering into from what. If you are entering into water from air, then the incident ray after refraction bends towards normal. If you are entering air from water, then the incident ray after refraction bends away from the normal, goes away from the normal. Okay. Basically, they retrace this path. So you cannot always take that after refraction it will bend. It depends on the medium. From which medium have you gone into which other medium? Okay. It depends on that. Okay. You will get to know later, okay, that this refractive index, it has to do with the speed of light. When you say the refractive index, it's sin A and sin R and mu2 and all this depends on the speed of light in different mediums. Okay, this is the ratio. For example, what have we done here? This is refractive index of water with respect to air. So, this mu2 in this case, so mu2, what is mu2? Let me be more specific here. This is the refractive index of water with respect to air. Okay. So this is actually equal to mu water air is equal to the speed of light in air divided by the speed of light in water. The speed of light in 1 is divided by speed in 2. Okay. So sin I kind of represents the speed in I, in this medium 1. Okay. So medium. Sin R, it is the speed in this medium. So that ratio will be the refractive index. For example, if I take glass, okay, if I take glass for example, okay, let's see, I have air here and then glass. So now, suppose light travels from air to glass. It's normal, right? Because you have a lens, the light travels from air to glass. Okay. Now, it travels here. So there is an angle of incidence. And instead of going straight, now it bends towards the normal. This is angle of refraction. So mu would be sin I by sin R. The speed of light in air is almost the same as the speed of light in vacuum. There is not much of a difference. The speed of light is pretty much the same in air and vacuum. It slows down a little bit in air, but it's almost the same as vacuum. Okay, so the speed here is this c, 3 into 10 power 8 meter per second. That's the speed. In glass, the speed would be Vg. Velocity of light in glass. It will be smaller than this. Speed of light is maximum in vacuum and air. And in every other medium, the speed of light is less. than the speed. Okay, so this is actually 3 into 10 power 8 meter per second, and this is roughly 2 into 10 power 8 meter per second. So 3 into 10 power 8 meter per second, and this is 2 into 10 power 8 meter per second. That's the speed. Okay. So now the refractive index, if you see mu of glass with respect to air, which is refractive index of glass. We generally don't refer to air or vacuum. Okay. So this is equal to speed in air or vacuum. So that is C by Vg. Velocity in glass, speed in glass. So that gives you 3 into 10 power 8 divided by 2 into 10 power 8. 10 power 8 cancels. So you get the refractive index of glass with respect to air or vacuum is equal to 1.5. So this is actually the refractive index. So basically the refractive, what you call as a refractive index, what you call as sin A by sin R, and all these things are nothing but the ratio of the speeds of light in the two mediums. Okay, so clearly why is light bending towards a normal? Look at this. So the sin A by sin R for glass must give me 1.5 all the time. So this numerator must be greater than the denominator. So if you have a bigger angle, bigger I, then you must have a smaller I. So sin I and sin R. So this must be bigger and this must be smaller. So if you make an I here, then you have to make an angle which is smaller than I if it is glass. Why? Only then you get 1.5. Okay? But look at the other way. Suppose I'm sending it from here, from water or glass to air. If we do it the other way around, then what happens here? Then in that case, what is the refractive index of air with respect to glass? That's it, right? The refractive index of air, the second medium, with respect to glass will be, now sin I will be this and sin R must be this. You know that now the denominator must be greater in the other way. If we were to do it this way, refractive index of air with respect to glass will be equal to the velocity in glass divided by velocity in speed in air. Okay, so this is a smaller number than this. So if this has to be a smaller number than this, clearly get this. Now this sin I must be less than that sin R. So this I will be smaller than R. So if I have 30 degrees here, after entering it may become 35 or 40 or 45. So then it diverges, like it goes away from the normal. Okay? I want you to understand this. But this is simply the ratio of the speeds in respective mediums. So usually glass, water's refractive index is 1.33. Okay. Glass and water and these things and other whatever you see, they have higher refractive indexes. Why do mean more than 1, higher than 1? Okay. So what it means is that light travels slowly in these mediums. Light travels slower in these mediums than it travels in air or vacuum. And that is why their refractive indices are more than 1. Because if you want to find the refractive index of glass, then It is refractive index of glass with respect to air or vacuum. Okay. The ideal definition is with respect to a vacuum. Air is almost the same as vacuum, so you are using these two things interchangeably, but the perfect definition is this. What is the refractive index of a particular material? Then it is the ratio of the speeds of light in these two mediums, vacuum divided by the medium. So then that becomes the refractive index of that medium. Okay. So that is the definition of refractive index. So clearly this is going to be more than 1. Refractive index is more than 1 of a material, of a medium, with respect to vacuum. Why? Because light has its greatest speed in vacuum. In all other mediums, it will travel slower than C. So, since refractive index is vacuum by medium, vacuum is always greater, and the medium value, the speed of light in the medium, will be less than this number. So, you get the refractive index which is more than 1 for all these materials. But when they travel from one material to another, things could be different. Right? If you want to find, I told you that refractive index of glass is 1.5, and then refractive index of water with respect to air, right? So that's why I'm not air or vacuum, so I'm not putting anything else here. This is 1.33. Okay. You see, this refractive index is greater than this refractive index. So, if I take a case where light travels from water to glass or glass to water, so what is going to happen? Suppose I have this case. The medium 1 now is glass. Then medium 2 is water. Suppose light travels from glass into water, and this is an interface, right? So I can draw a normal here. Now the ray will hit here with some angle. Incident ray. Then what happened here? Will it go towards the normal or away from the normal? They go away from the normal. Suppose if it was a single medium without, there is no water, it was fully glass, then it will continue in this direction, right? It will continue in this direction. Now I suddenly got water there. Notice that the refractive index of water is smaller than the refractive index of glass, which means that light travels faster in water compared to glass. When light travels faster in water compared to glass, then what is the refractive index? With refractive index of water with respect to glass, 2 by 1 is equal to speed in glass divided by speed in water. Speed in glass must be slower than speed in water, and that is why you got a bigger number, right, from this. So this is also equal to sin I by sin R. So this is a smaller number and this is a bigger number. So this has to be a bigger number. For this angle, this has to be bigger. So what will happen is that instead of going like this, then it would deviate like this. Okay? Now you notice into R is going to be greater. As I told you, if we reverse the direction, if we send light from water to glass, then clearly this is faster, this is slower. So now this will become sin I, this will become sin R. So greater angle, smaller angle. So that's what it will be. Okay. So hope you understand what refractive index is. Refractive index simply is a ratio of the speeds of light in two different mediums. So the refractive index of one medium with respect to the other, refractive index of one medium with respect to the other is speed of the other divided by speed of this medium. For example, we take water. If we want to find the refractive index of water with respect to air, then speed of light in air divided by speed in the medium. Or if you want to find the refractive index of air with respect to water, which means speed of light in water divided by the speed of light in air. So that's why you get this 1 by u2. And that also explains to you why the light ray either bends towards the normal or goes away from the normal. It has to make this work, because it depends on the speed now. Hope this is clear to you. I said, if I have two mediums and light travels at an angle and falls on the interface, and it's going to get refracted, and then you will have an incident angle and also a refracted angle of incidence, and also angle of refraction. So let me ask you this question. Okay, so this is interface, this is medium 1 and this is medium 2. So light travels here at a certain angle, and then it falls on the interface now. It's going to get refracted clearly. So I can draw a normal at that point. Okay, the normal is there. Then what happens is, supposing that this is a denser medium, optically denser medium, meaning that light is going to be slowed down here. It's going to travel slower in this medium than in this medium. Okay, so the optically denser does not mean that it is physically denser. Okay, some liquids, for example, okay, they are like turpentine. These liquids, they are less dense, physically, the mass density than water, but they have a higher refractive index, meaning that light slows down in those mediums. Okay, light travels slower in turpentine than in water, even though turpentine is not as dense as water. Water is more dense than turpentine. Kerosene, for example, 0.8. Right? That's the density. Water has density of 1. But then optically, situations could be different. So when I talk about density here, we are not talking about the mass density. We are talking about optically dense. Okay, a denser medium. So here I have an optically denser medium, meaning light will travel slower in this medium than in this medium. If it travels slower in this medium, clearly it will bend towards the normal. Instead of going straight, it will now bend towards the normal. Okay, we saw that. So I have an eye, I have an eye. So if I keep changing this eye, R will also change, then I'll get the refractive index of this medium with respect to this medium, the second medium with respect to the first medium. Okay, but notice here, so my refractive index is actually sin I by sin R. So this will keep happening for all these angles. But let us suppose that I am hitting, my light is vertical, it is through the normal, it's parallel to the normal. Suppose it's like this. My light is, suppose I take this way, another way. So what's the angle between the normal and the incident ray? It is 0. So sin I is 0. Then what should be this R? Will I have an R here? Suppose I take water and this is air. Let's say this is air and this is water. Okay? Or I'll say glass better. I said this is 3 into 10 power 8 meter per second. That's the speed, and here it is 2 into 10 power 8 meter per second roughly. That's the speed here. So the ratio 3 by 2 is 1.5. So the refractive index of glass is always 1.5. With respect to air or vacuum is 1.5 here in this case. So if I have an I value, then accordingly the R value will change. Right? This is what we discussed before. Suppose my I is 0. It is vertical. Okay? It's going through the normal now. So what will be the value of my sin I? Sin I will be 0. Then what is going to happen to my sin R? Will R have some value, say 1 degree, 10 degrees? Will it even have any value? If R has a non-zero angle, then my nu now will become 0. This calculation will go wrong. Because you know, the refractive index is the ratio between the speeds. It's always 1.5. But now I got sin I, which is 0, because this ray is going through the normal. Then what will happen to the refracted ray? What will happen to this ray? Any non-zero angle will result in mu being 0. The sin I is 0. So can it have a non-zero angle? Can it bend this way, that way? No. This ray will travel straight down. Why? Why? Because sin I is 0, then sin R should also be 0. 0 by 0, indeterminate. Okay? And remember, in limits and continuity, when you get 0 by 0 value, you go ahead and then find other ways of figuring out the limiting value. You don't allow 0 by 0 to be your answer. 0 by 0 is fine. Here also, I get 0 by 0. But does it mean that it doesn't have a refractive index? It does. The value is 1.5. So this is the reason, now you will be able to connect. This is the reason you say 0 by 0 is indeterminate. For this medium, okay, air and glass, you get 1.5. Suppose I have water here, then you should get 1.33. But then also you will have 0 by 0. Indeterminate. So 0 by 0 is indeterminate because you do not know what that actual value is. It doesn't mean that there is no value. There is a value, but you don't know what value it is. That is why 0 by 0 is called as indeterminate. Okay. So I can't find refractive index by sending a ray which is perpendicular to the surface, because the ray which is perpendicular to the surface will go straight, and sin A will be 0, sin R will also be 0. So 0 by 0, indeterminate. Does it mean that it doesn't have any refractive index? No, it does. It slows down here. The ratio is 1.5. But then I need to find it by changing the angle. Okay? What you need to understand is the ray that is coming straight into this medium through the normal will go undeflected. All other rays will be deflected. They will get refracted, and there will be an angle. Okay. Rather than going straight, now you see, there is a deflection here. Okay. Any other angle, you will have some kind of a deviation from the intended path. But when it goes through the normal, it will go straight down without any deviation, without any angle. So this is something that you need to understand. Okay. Okay. Next, let me take this case. I have a glass slab. Okay. Let's say I have a glass slab. It's made of glass. Okay. Now let me take a ray that hits the slab on this side. So this is my incident. So it hits the slab on this side. It's a thick glass slab, okay? So you have something like this. Okay, so it hits, let's hit it to that side. Okay? Keep getting it. Like that. So this is the slab, it's hitting it here. Now this is one medium, air is one medium, this is a different glass medium. So now light will go into the medium. The speed will decrease here. As the speed decreases, it will bend towards the normal because R has to be smaller than I. So what is the normal? This is the normal, right? This is the normal. So this is the angle of incidence. And if this was not there, the glass were not there, then this would have gone straight. Now that you've got the glass in its path, it is going to bend. So it should bend towards the normal. Instead of going straight, now it will bend towards normal. And once it is bent, then it will travel in a straight line in this medium. Fantastic. No issues. Now what is going to happen here? Here again, you see, there is an interface. This is glass, this is air, this is glass, and this is air again. Here, you have a normal here. So this is interface. Like this was interface between two mediums. This is also an interface between two mediums. So what will happen now? So I get this angle, right? So this is R, and this must also be R. Okay. Let's see actually the incident angle on this interface, which must be the same as the angle of refraction here. So then, if this was not there, if there was only glass and there is no air, then it would have continued without any deviation. It would have just continued without any deviation. But now, like here, so you see, once it deflected, it continued in the same line, right, until it met the interface. So if the interface was not there, then it would have continued like this, the same straight line. But now you have this thing, like the interface, what would happen? It should speed up, right? So what did we say? This would travel, if this was R, then the same I that you must have the I here. So this is I and this is I. Look here. If this medium was not here, then this would have traveled like that. The medium is here. Now it is traveling in a parallel ray, right? I could have drawn it like this. It will be parallel to this. Instead of traveling in this line, it is kind of getting shifted and then travels parallel to it. There is no, there's no angle between this and this. You can see that. If this is I, this is R. If this is R, this must be I. You see, then clearly this line must be parallel to this line. So this shift is called as lateral shift. Instead of traveling in this line, now it is traveling in a parallel line. So this is what is called as a lateral shift. Hope you understand this. Well, you may have noticed, when you looked into well in your farmland, if there is a well in your house, if you just looked into it, if you can see through the water is clear, then you don't really get the same depth, like if it is say 20 feet, 10 feet, or 30 feet. Okay. When you look at it, the floor would look like it is elevated. You don't see the 30 feet distance as you look into the water. And why is this happening? This is happening because of refraction. That's what we'll discuss now. Suppose you have a well or even in a utensil which is full of water. Okay? So let's suppose it's a tank. Suppose you have water up to here. It could be a tank or a well or a utensil where you have water. So it is like this. That's a height range. Okay. Now, let us suppose there is a coin, some object here. Say I just take a point. It's at the bottom, at the depth, h there. Okay. Let us suppose you are able to see it from here. How will you see it? I told you can see things only when the light reaches your eyes. The light from an object doesn't reach your eye, you can't see it. Why are you not able to see the back of my head? Only the front of my face, not the back of my head. Because light from there doesn't reach you, it's getting blocked. So you can't see it, even though you have perfect apparatus, the eyes. You can see the back of my head because the light is blocked. But then the moment I turn, you'll be able to see the back of my head because now the light reaches you. So likewise, I'll be able to see this coin only if the light reaches my eyes. Let us see what will happen to the light that is coming from this. Okay? Say, let me take the straight line, the normal, right? Okay, draw normal line. So light that is coming from this, the coin, then it will travel straight. When it travels straight, then this is medium 1, this is medium 1, and this is medium 2 inside. This is medium 2, and this is medium 1. So if light travels like this, then it will simply travel straight. It's better. I can remove this. So light travels like this. So light travels straight up. That won't get deflected. It will go straight up. But what will happen to this light? Okay, suppose there is a line. Okay, there is a light here. There is also a ray here. And there is also a ray here. Likewise, the other side. So from this point, the light rays are going in all these different directions. Everywhere. Okay? What will happen to this line, for example? So that will obey the law of refraction, clearly. So I will have a normal here. So this will be the angle of incidence. and I said this is water and this is air. So this is more optically dense than air. So light will travel slowly in water and then travel faster in air, resulting in, rather than going like this, continuing like that, it will now, you see, it will go away from the normal. Go like that. Likewise, this angle, rather than going like this, it will go like that. You see, this is how light will travel. Rather than going like this, it will go like that. This is how light is going to travel in all these different directions. Okay. Now, I am going to look at it from the top. My pupil, the eye, it's small, but it's not a point, right? It has a certain diameter. So, it is not just a light, which comes through the normal alone gets into me. Compared to, if you just look at it, my eyeball is something like this, let's say. This is my eyeball, okay, or the pupil of my eye, okay, and after that I have this eye, and it goes like that. My eye is like this, okay. So this is the pupil. I've enlarged it. It has a very, very small diameter, but you can see this. You can understand what I'm coming to say. So this light, this normal will go straight, that is all right. But normal is not the only ray that is coming and hitting my eye, right? So there are other rays, like for example this ray. There is a ray, it's coming like this. Okay. Coming like this. But that ray would have got deflected, so it's like this, right? So this ray has come and then it is going like that. Likewise, I would get another ray like this, this way. So you see, the rays in this small angle, they reach the surface and then deviate, and then the deviated ray goes and fills my pupil. So I'm just talking about that, the rays which fill the area of my pupil. So it's not a point. It's very small, but it does have a definite area. So in that area, I can have a set of rays, millions of rays. Okay, so they're bent like this. Now, how will I see it? If I see something, it is like, coming like that. See this? It's like this. You see, when you see that ray, it is like it is emanating from here, from this point. It's like that. In the mirror, that's what happens, right? When you see something, the reflection, when you see yourself, it is like you are there. It is like you are seeing a person over there. Actually, the person is here, in the mirror. But when you look at yourself in the mirror, it feels like the person is there and you are looking at him. Why? Because the light that is coming from you tells you that it is originating from there. So likewise, the light that reaches your eyes tell you that it is coming from this point. But where is the object actually? The object is here. But for you, it will look like the object is here, because it bends. So I'll draw it a little more clearly here. Okay, so like this. Okay, so this will be the set of rays from the bottom. Okay, instead of going straight, then they will kind of bend like this. They bend like this, and these are the rays that your eyes get. So it will look like they came from this point, not from this point. Actually, they came from here. But for you, it looked like they came from here. And that is why when you see something in water and when you put your hand to get it, you won't really reach that point, because your eye tells you that it is there, but actually the object is not there. The object is somewhere else. So how many times you may have done this? You see something in water, you put your hand to take it, but where you put your hand, the object is not there. It's slightly somewhere else, at a different place. Okay, so even though the body is actually here, the object is here, for you it will feel like it's here. This is what your eyes see. So this is what is called, this depth I'll call is as h dashed. This is called as the apparent depth. This is the actual depth. This is the actual depth. H is the actual depth. But then this is the h dashed. So apparent depth. You will note only this. And that is given, there is a relationship between this and this. You can derive it, but I am not going to do that. Okay. So what it means, how is it related? This h dashed and h. How are they related? Your h dash is equal to h and mu. That's the refractive index of this medium with respect to the other, this first medium. So h by mu 2, 1. This is 2. The refractive index of this medium with respect to that medium. That's what we'll see. Okay? I hope you are able to understand this. So this is the apparent depth. And this h is the real depth. So it will look like the body is not exactly at say 10 feet or 20 feet, it is slightly above, maybe 8 feet, 9 feet, or even 7 feet, not really 10 feet. So it will look like it's elevated. So that is the reason when you look at a swimming pool, the floor of the swimming pool looks like it is elevated. It's because this is how your eyes see things. Hope this is clear to you. When you see the sun in the morning, you say that the sun is there. Okay, it is rising. Okay. Actually, the sun is not there. The sun is still not risen. It is still below the horizon. But you will be able to see it even before it appears. So, assuming that I have a gun which will go, it's very powerful, and I can shoot long distances, any distance I want. So I wait for the sun. I want to shoot the sun. Okay, so in the morning I see the sun. Yeah, it has just risen from the horizon. Then I shoot at it. The bullet travels fast. But assuming that it will travel all the 150 million kilometers undeflected, straight, it won't hit the sun. The sun will be down and then the bullet will go above it. But for me, it will look like the sun is there. But when I shoot at it, the sun is not there. Likewise, in the evenings, you may still see the sun. It has not set yet. But actually, the sun has gone down. You will still be able to see the sun. So it's like this. You have the earth like that. Okay. Now, suppose we are here. Okay, we are here. The sun is okay. So this is your horizon. Horizon. Okay. If the sun is here, suppose the sun is here. This is the sun. See, you can't see it. Right now, you can't see it. Right? That's what you would think. But then the earth has an atmosphere. Okay? So the earth has an atmosphere. I'm just drawing it for so it is becoming more and more dense as you start from the top and then as you come down. So it will be light here, dense here, more dense, more dense, more dense, more dense, most dense at the sea level. Because all the weight of all the molecules are piling up here. Like so at the sea level you will have the densest air, densest atmosphere. Okay. And on the top, clearly, it will not be that dense. So what happens is, in this case, the mass density corresponds with the optical density here, it's the same way. Okay. So what will happen is, light, the sun is down. So if the atmosphere was not there, you can't see the sun because it is down. You can see that. But now the sunlight, comes in. It goes in all different directions. All different directions. It goes there, it goes there, it goes there, everywhere. Let us suppose there is this. So you can't see it. Okay? You're here, you can't see it. It's down. So now what happens is then some ray that is going out of, it was not intended for you. It would have gone somewhere there, maybe this way. Okay, it would have gone somewhere there. It would have gone somewhere there. But what happens is, now it's entering the atmosphere. The atmosphere, so you see, from vacuum to the atmosphere, like you're entering now. So clearly, it will be slightly slowed down. And then the density of the atmosphere increases. So then what happens is, so there's a normal. So if there's a normal, suppose this is a normal. Okay. It's a normal. Okay. I'll put it this way. Normal here. Okay. So you see, now it is becoming dense. So what will happen? It will bend towards the normal. It will bend towards the normal. Now it gets into the next layer. Then that also has a normal, like that. Now what will happen? It will bend towards, bend. And then finally it will bend and then reach you. The ray that should have gone straight now is bending and reaching you. Okay? Now since it reaches your eyes, what would you think? You will think that the sun is here. Just this is the angle at which you see it. So you will think that the sun is there. But the sun is actually here. So if you shoot the sun, then the bullet will go past it, it won't hit the sun because the sun is here. And the same thing happens to you when the sun sets here also. So you will be able to see the sun long after it is set. Maybe I don't know the number, I think maybe like 10-15 minutes within that time, you will still be, I don't have the number right now, I may be wrong here. But you will still be able to see the sun, say roughly 10 minutes after it is gone, so below the horizon. The sun is not exactly there, but you'll be able to see it. It's because light bends, it enters the atmosphere and bends and reaches you. And it gives you the illusion of the sun being there when the sun is not exactly there. This won't happen on the moon. Okay? Because the moon has a very, very, very thin, no atmosphere at all. Next to nothing. The atmosphere of the moon is next to this. You don't have. For all practical purposes, you have no atmosphere on the moon. So this won't happen on the moon, but this will happen on the earth. So on the moon, when you see the sun, the sun is there in the morning or in the evening when it rises or it sets. But on the earth, in the morning, when you say that the sun has risen, the sun has not risen yet. It is still below the horizon. And when you say that the sun is set, the sun is still, it has not set yet. No, it has set already. But you will still be able to see it. Because the light from the sun bends and reaches you. And then you think that it is somewhere else, while it has already gone below the horizon. So that happens to you every day. And this happens because of diffraction of light.